Is it 2018 already? Postdoc, the New Orleans ACS meeting is coming up. I need data. Again. Yeah, I got a little bit of data to present, but I really need some new equipment. New equipment. Well, time to make it rain.
Damn. Yeah. Yeah. Yeah.
Woo! Nice. This is awesome. You have no excuses now.
Yeah. Yeah.
Hello there. How are you all doing? Welcome to another episode of Ask Us Anything About Electrochemistry. I'm Dr. Alex Paroff. My colleague Neil is out this week and probably for the next few weeks. But I'm here holding down the fort, trying to make sure that we're still able to answer as many questions as we can about electrochemistry. Now, granted, I'll be honest, Neil's the expert when it comes to EIS and batteries, but I will try my best to answer your questions. For those of you who are new to this live stream, my colleague Neil and I, Pine Research Instrumentation, we get a lot of questions, either from our YouTube comments or from webinars, emails, telephone, just a lot of electrochemistry questions. And so what we wanted to do was create this format where you could ask us anything you wanted about electrochemistry, and we have a chance to go into a little bit more depth into answering some of these questions, more so than, say, just a typical Q&A session. We are using Restream as the platform to broadcast this onto YouTube, and we find that there's maybe about a 10-second delay, maybe 20-second delay at most between what you type into the chat and what I'm able to see on the screen. So as such, just keep that in mind as we get questions. And actually, as I think about it, most of the time, once I get a question, it usually takes a while for me to answer it, and so I can see all the upcoming questions and stuff that come up. If you're watching this after the live stream, I will have the description, all the questions in the description below. So if you want to, sometimes a lot of you watch the live stream after it's gone live because you can't make it for whatever reason, just timing, lots of time zone differences. And so hopefully within a few days, I'll be able to get all of the timestamps in the description below so you can find the questions and find the ones that are most relevant to you. We'll go for at least 2 hours-ish, maybe a little less, depends on how many questions we get and how long it takes to get through them. It's just me operating this time, so normally it might take a while. We'll see how far we go. Lastly, two last things. There are no dumb electrochemistry questions. You can ask anything, and whether I'm able to answer that or not will be up in the air. But overall, I'm hoping to. You can literally ask anything, even the simplest of electrochemistry or more complex of electrochemistry questions. And lastly, I'm going to apologize ahead of time if I mispronounce anybody's name or anything of that, or whatever you put into YouTube. Okay, so with that being said, one thing I usually like to ask is whether or not people can hear me. Is the audio good? I'm just also doing just some troubleshooting, some testing as to whether or not you can actually hear what I'm saying. And so let me know in the comments if you can hear me. But otherwise, I will we'll start answering some questions that you guys have put into the chat. All right, so Sakaria asks, please elaborate EIS analysis for supercapacitors. This is very good. This is a very good question. So Sakaria, I actually have not worked with supercapacitors personally. I just did like a very kind of quick view, just kind of looking online about like supercapacitors and what they do. But I will tell you, generally speaking, one thing to keep in mind is, and I'll just draw this, let's see, hold on, let me just draw this on here. So if I just draw, I'm just going to share my screen. Hopefully you can see, I just have just paint on basically. But generally speaking, I don't know enough about supercapacitors and their design, but I would imagine, but all capacitors in their design have some kind of some charge on, two parallel plates with some charge on it. There's some kind of dielectric in the middle. We'll just use this this green thing to represent the dielectric. And then going back, we have some charge on the other side. And it's not through it. It's actually a better picture would actually be like this. So let me actually erase that and actually put the marker on the other side. So it's charge on one side, charge on the other side. separated by some kind of dielectric. And so that is a capacitor in short. So supercapacitors, I imagine there's some form of this, or maybe there might be things like, I don't think so, but there may be some membranes or other things in the middle. But generally speaking, when you're using EIS to analyze your supercapacitor, you'd hook your potentiostat. One side would be like your working sense on one side, and then you'd have a 2-electrode setup. You'd use a counter electrode / reference on the other side. And then you would do your EIS analysis, you would do your EIS experiment. And let's say you had a Bode plot. You'd have Z real on the x-axis. You'd have negative Z imaginary on the y-axis. And then you might have some, some semicircles. Maybe you have a diffusional tail or something like that. I'm guessing more often you'll probably have something that is going to look a little bit, maybe it's just like one really big semicircle. And usually this is the case, or more accurately, you may have something, if it's a true capacitor. If it's a true capacitor, then you'll have more of like just a straight line going up. So if you were to do impedance of a capacitor, just a pure capacitor as your circuit element, it would just be a line starting from from a high frequency. So this is when you have high frequency. Can't spell. And then you have low frequency here. Okay. So from high to low frequency, you get something that looks like this. Now, really, this is my assumption, is that you would just have a capacitor. Maybe it's a supercapacitor. And then what you would do is you would just do circuit fitting of a capacitor associated with this kind of data, is my assumption. And then you would fit it to figure out what is the capacitance of your capacitor. That's at least my assumption about the use of EIS for analyzing supercapacitors. So I don't know exactly how helpful that was. Hopefully it was somewhat helpful, but that's how people do it. If you want more elaboration, I'd be more than happy to elaborate more on that. So let me just check to see. Let's see if there's anything. All right, checking that. Kanav, good to see you. Good to hear from you. Yeah, if you want to, drop me an email of the manuscript that you're looking at, I'd be more than happy to take a look at that. All right, so just kind of going in order as I receive them. Okay, Priya is asking, hi, how does applying bias affect the position of oxidation and reduction peaks? This is a great question. So I'm assuming this has to do with cyclic voltammetry, and please correct me if I'm wrong about its possession, but what you're talking about, and again, let's share a screen. Let's just let's go back here. But what you're talking about is you have a cyclic voltammogram where you have your voltage or your potential, you have your current, and then you have some kind of oxidation and then some kind of reduction. And you're wondering about the peak position, right? Oh, let me use green. The peak position here and the peak position here for the oxidation or the reduction based on the potential that's applied. Okay, so, sorry, I feel like I have a sneeze coming on. So basically, the applied potential, the bias that you apply, should not have an effect on the peak position. That's kind of how it is. That like, whether this is a scan rate, but the position of these peaks does not have anything to do with where the peaks show up. Those peak positions are going to be based on the fundamental properties, the intrinsic redox potential of your molecule or your species. It may play a role, the reference electrode you use might change it. The scan rate might change its position. If you have solution resistance, that will certainly change the position. But the application of a bias should not affect the position of your oxidation and reduction peaks. So prior, I hope that is, I hope that's helpful. I hope that answers your question. And let me know if you need more clarification. Let me zoom ahead and see. Hold on one second. I need to get a tissue because my nose is running. So hold on for just 1 second. Oh. All right. Sorry about that. Oh, sorry. I think I just have some kind of like runny nose right now. Let's see. Okay. Didn't lose anybody. All right. Let's take a look at the next question. During the experiment, after CV performed at different scan rates, should we use a new fresh electrode for GDC test? So, that's a good question. This is from Sandeep. Oh, my nose is just running. So, this is a good question, and it's a little bit hard to tell, but generally speaking, some molecules that you're doing a CV experiment with, doing scan rate studies, you will get some level of irreversible adsorption on your electrode surface. And so if you get some of this irreversible adsorption on your electrode surface, then it's probably a good idea to not necessarily use a fresh new electrode for a GCD test, but to simply polish your electrode prior to doing the GCD test. I believe that's galvanostatic charge discharge experiment. And you will observe this if you actually do several cyclic voltammograms on top of each other. Does the current start to decrease? Does it get smaller and smaller, meaning that less current is passing because more of it's kind of just getting stuck onto the electrode surface? So that would be the indicator, I think at least, as to whether or not you should use a fresh electrode for a GCD test. But honestly, if the chemistry is the same, then whether you polish or clean your electrode before doing one test or another, the results should be similar. So Sandeep, I hope this was helpful in doing this. Let's see. Make a video about ammonium ion battery as a lab tutorial. I might ask my colleague a little bit more about doing some more battery tests for tutorial videos. We'll see if I can get to it. What technical issues arise during CV and GCD? So there can be a lot of different technical issues that arise. There's no shortage of troubleshooting problems that you can run into just based on, well, you're doing a battery related experiment, so it's not necessarily, but at the same time, you also mentioned should use a fresh electrode. So like that makes me think that you're not necessarily always doing a battery experiment. But so Sandeep, maybe if you want to maybe if you want to give me a little bit more information, if you're actually doing like traditional 3 electrode cyclic voltammetry, or if you're just doing electrochemistry on a battery, because normally, to my knowledge, a scan rate study is not done on batteries. It's just charging and discharging, and it's not necessarily how fast. I mean, maybe it actually is like how fast can you charge or discharge your battery, but that's usually not a function of the scan rate in like a CV. So, but there are a lot of technical issues that can arise, and I'm hoping that you'd be the one to ask me what technical issue you may or may not be running into and how to solve it. Okay, Knav asked something. Thank you. Good. So Knav says hello. All right. How do we calculate? Let's see. How we calculate charging, discharging performance over a number of cycles? I actually don't know. Neil would be the one to determine. He would know the performance. Like you're saying, calculate performance. Well, I think the performance isn't necessarily like a number or something that needs to be calculated. It's more like, okay, how many cycles are you able to perform while the battery still maintains its the same potential? Or is it not reaching the potential every time? Like when you charge it after the 50th cycle or the 100th or the 10,000th cycle, oh, now the battery, its capacity is lower. Or the rate, how long it's taking to charge might change. So I think there's a lot of factors involved in determining the quote performance while doing a charging, discharging over a certain number of cycles. So I think it depends a little bit over exactly what you want to do. Neil would probably know a little bit more about looking at, say, the total charge, like if you charge a battery at a specific current, say like 1 milliamp, how long does it take to charge the battery? And that way you get like, the capacitance, but you're also getting, you're figuring out, oh, it's taking longer to charge the battery at the same rate after so many cycles. And that goes into its, its performance or evaluation of its performance. So Sandeep, hopefully this is helpful. Let me see if there's any more kind of questions. You have another question here. But I'm going to get to the next question that's come up. Okay, so this is from Martin. Hello, I'm Martin from Brazil. I'm facing a situation where I use copper nanoparticles and SB. That's not tin. I don't remember what SB chemical symbol. Antimony, of course. Has nothing to do antimony and antimony nanoparticles on a glassy carbon electrode. However, I would like to further investigate the formation of oxides during CV. Is that possible? Yeah, I think so. I think it depends a little bit what exactly you're trying to look for in oxide formation of oxides on these nanoparticles. So you can definitely use electrochemistry to do so. The question is how. So I don't know very much about antimony, or I know a little bit more about copper, but some of these oxides, you can do electrochemistry. You can find the open circuit potential where nothing is happening on your nanoparticle system, nanoparticles deposited on your glassy carbon electrode. And then you can look at the oxidation, so you can look for an oxidizing current or the potential with which oxidation is occurring. You can also look for the reduction of oxides. So let me at least give you an example of that using cyclic voltammetry. So if we go back to my little presentation here, let's delete this. So just to kind of paint the picture, you have some kind of I'm assuming you've got this is your electrode. You've got like a glassy carbon disc here, and then you have you got some nanoparticles on your surface. Little guys here. Maybe they're all clustered up. Stuff like that. So that's what you have. Okay. Now, when you want to do cyclic voltammetry, okay, you have your voltage, you have your current, and you want to look at oxide formation. So you're looking at these kind of like copper going to some kind of copper oxide, something along those lines. And there's some electron transfer. If you're using IUPAC conventions, positive current means oxidation. So as you're sweeping the potential kind of back and forth, you're looking for instances where you're going to form positive potential. So if I started here, maybe this is 0 volts. Oops, I want that. So maybe this is 0 volts. Sorry, just wipe my nose quickly. You might find that oxides will form at different potentials. So maybe oxides form at one potential, maybe oxides form at further potentials. So this information is actually very helpful when you're trying to determine, what are these oxides forming? And if this is anything like, say, platinum, for example, when you sweep the potential back, you might see a reduction. This might be a reduction current associated with the reduction of your oxide back to neutral, to the neutral metal, to the neutral copper or antimony nanoparticle. So that's something that you can actually look at in the cyclic voltammetry. So that's one way, you can look at. You can look at, what's the onset potential for your nanoparticles. And that actually gives you some interesting thermodynamics and some interesting ways to study nanoparticle formation on your thing. So hopefully that is helpful, Martin, and you can ask me for more clarification and stuff like that. It's good to see Neil. Neil is here. Can't take questions. Let's see. He will try to answer some questions once he's able to join the live stream again, which may be a while. So we'll keep an eye on some of the questions that come up. Oh, Neil may or may not be joining us from the airport, possibly. But we'll wait for if Neil's gonna make it or not. So we'll see. Let's see. I wasn't sharing the screen. Holy cow. Thank you for pointing that out, Neil. Let's see. So my screen was not being shared. Share screen. So this whole thing from before. All right, can everybody see that I've got this picture? That's rough. He's got you might try to come online. Okay. That's really weird. Okay. Oh, you know what's happening? I know what's happening. That's what's happening. I had the maximize button on. Sorry. While yeah. Hold on 1 second. I will come back and explain this one more time. My nose is running like crazy. Okay. I'm sorry about that. Let's see. Just always a lot of issues going on. But let's see if I can still let me try to get back to Martin's issue here with copper and antimony nanoparticles. If we go back, what I was describing was this is your electrode here. Glassy carbon, you put some nanoparticles on the glassy carbon surface. You then have your voltage versus current. And let me actually just erase this so I'll just go back to this. Just do this one more time. But basically, you can study the oxidation process if you do cyclic voltammograms, and you get multiple voltammograms where, say, this is your oxidation current. This is the IUPAC convention, so positive current is oxidation. As we go to positive potentials, you get oxidation. So you may do multiple, actually, erase that one. But you'll have multiple voltammograms, and maybe they'll go different onset potentials. And so these different onset potentials will give you some information about studying the oxidation of your copper or copper oxide or antimony nanoparticles. And similarly, as you sweep the potential back, you'll see hopefully some reduction of the oxidation current, or the copper oxide will go back to forming copper on your electrode. So this is, at least just very briefly, hopefully an explanation as to what is happening, or a way you can study the formation of oxides on the electrode surface. All right, so let's see. Sandeep is asking, how do we draw potential versus capacity curve? What factors affect EIS testing, and how we can fitting curves? So actually, I don't know how to draw a voltage versus capacity curve as much as it's just like, oh, on one side you have voltage and one side you have capacity, or vice versa. I have seen some types of plots where they do have the capacity as a function of voltage. I don't know how those are generated, so I don't know how necessarily to draw them. And you're asking what factors affect EIS test, and how can we fit curves? So there are many factors that can affect an EIS experiment. Reference electrode, the amplitude, the stability of your system. It can be a very complex technique, both from an analysis and understanding side, as well as technically what is happening to your system while you are performing it. The configuration of the cables can also play a role, Sandeep. So all those things can play a role. Now, when it comes to fitting EIS curves, you will need to just use some fitting software. And Pine Research does have EIS tools for fitting. And so hopefully I can show you. I don't actually have any. Let's see if I have any. I don't think I have any EIS data per se, but let me see. I think I have some sample EIS data from somewhere. But what you'll want to do eventually is, take some kind of plot. This is a Nyquist plot. This is EIS data. And then you're going to want to do some kind of circuit fit. And you'll need to find an adequate circuit model that you believe is representative of your system. And I know that this one, at least, is, I wasn't pretty sure this is the one that does it. So this is how you would circuit. You'd need to get some software, insert your data, start, and then start like fitting and adjusting and playing with the circuit fit and the circuit fit parameters, and then you'll be able to get, some results, some interesting values for, your capacitance, what your resistance is, and things of that nature. So that's what you need to do. I don't know if there's a way outside of it, but that's what you do for your system. Okay, all right. Hello, this is Hiranmoy. I hope I got that right. From India. How has LOD been calculated for sensors? What? LOD, I believe, means limit of detection. So the limit of detection It's more of like an analytical. Sorry, my cable always gets a little confuddled with the my chair. The limit of detection will be based on several things. One is going to be the instrument itself. So the instrument that you're using, let's just say it's a potentiostat. Potentiostats have various electronic circuit components that have minimum specifications for what they can measure. So most of the time for sensors, the current is the thing that you're measuring, because you can usually relate concentration to current. Well, maybe nanoamp or picoamp currents are the lowest amounts of current that your potentiostat can accurately measure, just fundamentally based on how the instrument is made and designed. And I could get into a lot of detail about how potentiostats work and how current ranges, where they come from. So that's one thing. There's the instrument. But then when you have your sensor itself, that is selective for the analyte that you're trying to sense, what you'll probably need to do is continue to decrease the concentration of the thing that you're sensing, and then see whether or not your instrument can accurately measure it. And I think the accuracy of the measurement will be very important in this, in what you're doing, because maybe you measure it kind of, but maybe it's not accurate. And when I say accurate, one thing to keep in mind is that your signal to noise is also going to be a big role. So with potentiostats that can measure nanoamp current ranges or current values, very, very small, sometimes there's so much noise in the system, just the electrochemical system, that you have something there and it's showing up, but the signal to noise is so low that it wouldn't give you an accurate value for the for what you're trying to detect. So hopefully, Herenmoy, that is helpful or helps you determine how to determine the limit of detection. Oh, I don't know if it's like the temperature changed like dramatically recently. We're in the Carolinas, so we had some hurricanes weather, and it was hot, and it got cold, and for whatever reason, I'm just blowing my nose very hard. Okay. Okay, Martin. I don't think it's sharing. Okay. So Martin, I see what you wrote. Did you see? I tried resharing the screen a little bit earlier to show what I think about like the nanoparticle and antimony sensors. So did you? Please let me know if you saw that or not. Otherwise, I can redo it. Okay. Moving on with some of these questions. Hello, this is from Mohammed Salman. Hello, what is the maximum glucose concentration limit that can be measured by an electrochemical nanosensor? Like especially in a zinc copper based, which type of nanosensor gives the highest limit? Or I think what you mean is, So I am unfamiliar with the use of zinc copper nanosensors. What I imagine is that zinc and copper are particularly sensitive to the detection of glucose. And so what you're looking for is the maximum glucose concentration limit. So I think I need a little bit of clarification, because most people are looking for the lower limits, how small a concentration of glucose you can measure. But some people are looking for like, okay, well, what's the highest concentration of glucose you can measure? So it will be based heavily on the nanosensor and its geometry, its configuration, just basically how it's tested just empirically. So if you can reproducibly create the same zinc copper based nanosensor and continue to make that kind of electrode, then you can test it in a glucose environment for the current associated with, say, glucose, because usually it's not like glucose doing electrochemistry. It's like glucose oxidase or another something that glucose is in equilibrium with, like glucamate or something like that. And that is electroactive, and you can usually figure out what the concentration of glucose is from the concentration of the other thing. But the highest limit measured will also, well, so I think you're looking for, like, can you detect, say, a supersaturated glucose, supersaturated levels of glucose and get accurate concentrations. So the truth is, I don't know, but hopefully I'm giving you some hints as to how you can determine what it is. Your sensor also, electrochemically, will be based on the electronics of your instrument, and those also have a limit to it. So if, for example, you're doing some, the kind of current that you measure and the electronics used to measure the current in an electrochemical system are usually linear. So as the concentration increases linearly, so does the current. But sometimes you might reach a point where the current will start to plateau or it won't match with the actual concentration. So that is an instance, sort of say, where maybe the maximum glucose concentration is very hard to measure in a way. So Mohammed, I don't know if I'm able to really answer your questions super well, but hopefully that kind of gives you a thing. It's a very specific question. Unless I was studying zinc copper nanosensors, I wouldn't know what the answer is, or what's the highest concentration of glucose that you can measure. Okay, let's see. From Carlos. Hello, I'm working on immunosensors with screen printed electrodes. The supplier recommended using the ferrocyanide solution for EIS and CV. I might need DPV, differential pulse voltammetry, too. Can I use the same solution? So the answer to that is absolutely yes. So the ferrocyanide, actually all of the experiments that you just mentioned, Carlos, they're all in the same electrochemical cell, the same screen printed electrode, the same everything. All you're doing is just pushing a set of different buttons on your potentiostat to do EIS, CV, and differential pulse voltammetry. So you can absolutely perform all of those in the same solution. You don't need to prepare a different or a separate solution for CV versus EIS versus DPV. So I hope that answers your question. Please let me know if you need further clarification on that. Okay, so going now. Let's see. Question is from Sukanta. I hope I got that right. Sukanta. During cyclic voltammetry study in homogeneous media, if we gradually increase the surface area of the counter electrode, then during sweeping the potential, can we get more current? So that's a good question. That's actually a very good question. So in principle, the area of the counter electrode should not matter in the grand scheme of things. If you're getting some kind of current at the working electrode, if you were to continuously change or increase the area of the counter electrode, you should not get more current from the working electrode. This assumes that the counter electrode is already a very large size. So what happens is so the surface area of the counter electrode. So if the counter electrode gets bigger, the surface area also gets bigger. That shouldn't affect it. Now this is assuming it's already big. Now the way potentiostats work is that the counter electrode kind of applies the voltage. It drives current through the electrochemical cell, and for a counter and a working electrode, in any electrochemical system, the charge must be equal. It must be maintained. Like charge balance has to be maintained. So any charge generated at the working electrode must be equal to the charge generate the counter electrode. And because we only care about what's happening at the working electrode, we usually make it so that the counter electrode is so big and current can flow very easily that it never becomes a limiting factor to what current we generate at the working electrode. Now, if the counter electrode is too small, you'll usually get a compliance voltage issue. Now, it's got to be like maybe, the working electrode has to be maybe like 5 or 10 times bigger than the counter electrode for this to be the case. It also is going to be dependent on your potentiostat. So generally speaking, if you increase the area of the counter electrode like a lot, it shouldn't actually play a role. You want the current limitation to be based on what happens at the working electrode, because your analyte and your analyte's concentration should be the only thing that governs the amount of current. The counter electrode should in principle be able to generate limitless, current by comparison to the working electrode. So I hope that makes sense, Sukanta. Please let me know if you have any further questions or further clarification on that. All right. All right, so this is from Jam 2022. So, hello, sir. Can you explain what is the appropriate mechanism of galvanostatic charge, discharge, and a supercapacitor? I think that's what you mean. Well, let me actually see. GCD. Maybe I don't have that right. So, GCD supercapacitor. I want to make sure I know what you're talking about. Yeah, so GCD, galvanostatic charge, discharge. And then you have a follow-up that might be related. Sir, in CV, we are applying positive bias to the electrode. Then how to current comes in negative during reduction? I think I need a little bit more clarification about this question. What you said makes sense. It's like, okay, when you apply a positive bias to the electrode. Oh, so I think I know a little bit what you're talking about, Jam, in this one. So first off, I don't know exactly what you mean by the appropriate mechanism for galvanostatic charge discharge in supercapacitor. What do you mean by the mechanism? Because galvanostatic charge discharge is a technique. It's using it's doing a constant current experiment where you're applying a constant current and you're seeing the voltage increase or change as a function of time, and then usually people are cycling that kind of result, that data. So when you say mechanism, I'm not 100% sure I know what you mean. I also don't know enough about supercapacitors and what they do and how they work. I just understand regular capacitors, and even that I only understand it a little bit. But I mean, what's happening when you're galvanostatically charging and discharging? Maybe that's your question. What's actually happening? Is Neil has described this before in the past, but your battery has like these lithium-ion batteries have lithium ions that are intercalated into a lattice. I believe it's a carbon lattice, and that's when it is quote discharged. That's when the battery it's like thermodynamic normal state. And what you do is you charge it. You're basically applying a potential to get the current to move in the opposite direction, getting the lithium salts back on one side, and you're getting the carbon on the other anode or cathode. I think it's anode, to be on the other side. So again, I'm not a battery expert, and this is a supercapacitor, but that's usually like what's happening. You have ions moving from one side to the next. Capacitors typically, depending on how they operate, capacitors are just these two big parallel plates of charge with a dielectric in between, and the charge is not allowed to combine. But usually, like, the power flows through an external circuit to make them quote neutralize or combine. That's where you get the power from a supercapacitor from. So I don't know exactly the appropriate, like what you say when you say mechanism. So I might need a little bit of clarification there. Okay, so this question, I think what you mean, and let me share my screen because I just apparently know cyclic voltammetry. And let me just make sure that it's showing up. Yep, so let me clear this. So select. So I believe what you're referring to is if you have a, this is voltage, and let's say we have like 0 here, and let's say we have like +1 here. And you do some cyclic voltammetry. Okay, and let's say this is like 0 current. Your question for the most part, 0. Nope, that does not look good. You have 0 current here. And your question to a degree is like, this makes sense to you conceptually. You have a positive potential, you have positive current. But what doesn't make sense is you have positive current, you have positive potential and you have negative current. So, and please let me know if this is what you mean. So the current is negative in the reduction because this usually has to do with a homogeneous diffusion of ions in solution. So current would flow in this direction associated with the thermodynamics of the molecule of the species. And so this is like a mass transport related problem. You have these, if you look at kind of the surface of an electrode, you have some analytes at the surface, and there is an electron transfer to these analytes. I'll just use yellow here to kind of indicate electron transfer. So the concentration of all these species, this current, this electron transfer occurred, that's all here. But this happens at a potential, maybe it's like 0.5. Well, anything below 0.5 is not thermodynamically favorable to have this species. So all of a sudden you get current flowing back. You have, you have a reduction, sort of say, or actually it's going this way. So if it's a reduction, the electrons are going from the conductive metal surface to the molecules or the analytes in the solution. So this reduction, metal going to here, is just the opposite of what's happening here. Sometimes we commonly get confused with what it means to have like positive and negative potential. But even if we have a positive bias on the electrode, we can still get a reduction if we can still get reducing current even though it's a positive bias, because it's still not sufficiently positive a bias to keep the electrons in the oxidized state. It's now more favorable for them to be in the reduced state. So hopefully JAM 2022, this kind of helps you a little bit. Please let me know if you have any questions or need additional kind of clarification about some of these questions. And I may be going through some of these questions very quickly because I don't have Neil here to kind of balance it out, and I can look at questions and give you more time. But I hope that some of these answers are helpful. Okay. One thing as we wait for any more questions that people might have is we do get, there was a question way early. And actually, let me have a sip of water. I might not actually be able to find that question here. Yeah, so there was a question from King of Chemicals before the live stream started, which had to do with, I have to get it here because it doesn't show up on YouTube, or it doesn't show up on Restream here, and that has to do with the parameters and figuring out what kind of information you get from, say, a Nyquist plot or the stability of the capacity of let's see, how to calculate the integrated area of time versus current under discharge curve. So let me write that down. I will put that in as one of the questions, and this was from King of Chemicals, and he just asks how to determine area under the curve for current over time. And then let me share that so that you guys can at least see what this question is and how we can solve this question. All right. So let me. Oh, actually, I want to go to Aftermath software. So let me just make sure you all can see it. So actually did a little bit of this, but let's try it again. So if I have a voltammogram, let's say I have this cyclic voltammogram. What you're going to want is you're going to want to get the current. And I'm going to remove this tool so I can show you. Let's see. So let me go. So I already did this earlier, but I'll delete the tool. Can I delete the tool? Okay. So this is the current over time. So when you get your voltammogram, your voltammetric information, you should also have access to other information such as the current over time. And if you don't have a plot like this, it's not that hard to get it. If you know what your, you have all your current values here, and then you know the voltage, you know when you started, you know the voltage as a function of time because you know what the scan rate of your experiment is, you could produce a current over time plot. And really, you just want to get the area under the curve. And in this case, we have a reduction. So what I want to do is you can actually import this data directly into our Aftermath software and then use add tool. There's an area tool. And it's a little bit of a weird tool, slightly wonky sometimes. But you can define the area that you want to study. So for example, I just want all the reduction current, how much reduction was happening. Well, I can actually go here and just say, all right, well, at zero current is kind of where I want to start. And if I just make some adjustments and also see, all right, how far, all right, so my baseline here is basically 0. I can adjust it ever so slightly. And I want it from the start. And this is basically, I might want to go a little bit further. I mean, this is actually in the part of the voltammogram where, I'm starting to go back to oxidizing, oxidizing my species. So I might want to go something like this. Like this is all the current that's associated with the reduction, in this case, of ruthenium hexamine. And I get this value of minus 155.8 microcoulombs. So that was the charge, a combination of Faradaic and non-Faradaic charge. I'd have to do some further work to figure out, okay, what is my double layer capacitance and the charge associated with that. So I know that most of this current probably is not double layer or is double layer charging. I can get rid of that. But this is the way you would just use an area tool in a program or software like Aftermath and do some estimations about what's the total charge over time within the bounds that you want. This is actually where the potential switched. You can kind of tell based on this little, it's a little weird blip in this area. But this is a way you can get the area under the curve and the total charge for the current versus time. Now, and this is free software, so you can download Aftermath from the Pine Research website for free and actually start doing some of these calculations. All right, so it looks like we may have some extra questions. Let's take a look. Okay, so Said and King of Chemicals actually gave me some information. I want to get to King of Chemicals. Sorry, I correct my question, King of Chemicals. Let me see. How to calculate the integral area of voltage versus time for the discharge curve for each galvanostatic charge discharge curve plateau. Interesting. So when you do, so I think the procedure, King of Chemicals, would actually be about the same in the sense that when you're doing galvanostatic charge discharge, you are setting the current. You're setting it to say 1 milliamp or 2 milliamps or 500 microamps, however long, or the rate at with which you want to charge your battery. And what you measure is the potential as a function of time. And you'd kind of use the same thing. So you would get a voltage versus time plot, and that could be done, at least in my case, you would do a chronopotentiometry experiment if you were using Aftermath software. And then you would still use, if you wanted the area, you could still use the area tool. So I think that would still be the way of getting like voltage. The integral area will tell you the total, well, voltage over time. I don't know what that gives you as kind of a scientific quantity, sort of say. Like current over time gives you charge, but the integration of voltage versus time might be a little bit hard to find out. But King of Chemical, I hope this was helpful, at least a little bit. Please let me know if you have more clarification. If you want me to look at some of your other questions, I can go back to some of your other questions. So let's see. Let me get to so Saeed had a question, and I'll get to some of the other questions that just popped in. When electrode deposition method is used for extraction of a metal from leach solution, how we get to know that which potential should be applied? Oh, okay. All right. So I think this is a pretty good question. So for something like this, electrodeposition, so Sayed, I hope I'm getting this right, but it sounds like what you have is, let's just go back to our little presentation here. And let me make sure that it's showing up. Yep. All right. So I'm going to just delete this, delete that. Okay. And delete this guy too. So what it sounds like you have is you have some kind of solution, right? So you have some kind of solution, and it's got a gamish for all intensive purposes. It has a mixture of lots of little different things, you know, different analytes, different things. And you are interested in doing electrodeposition, right? Maybe it has different things. Maybe it doesn't have different things. I might be incorrect. And you have an electrode that's in solution. Okay, and let's make this electrode like, well, yeah, this color works. So let's make it. Oh, actually, that didn't work. It looks a little strange. I should be able to actually insert just a shape. So let's just make the electrode this block here, and we'll make it gray. Okay. So this is the electrode. And your question is basically, what's the potential? Like at what E naught do I need to apply to get electrodeposition on my surface? Oh, King of Chemicals, the software, right? Let me just write it. Can be found. And you should be able to download our Aftermath software for free. You just need to create an account, which is also for free. But anyway, so you have, and there are 3 other electrodes. Let's just say, you know, you've got a reference and you've got a counter. They're not as important in this picture, but you just want to know what potential you want to apply. So actually, the best way to determine what potential to apply is to do a cyclic voltammetry experiment. And if you're doing electrode deposition, you are looking for the reduction of your metal or whatever the species is. You want the reduction, so you may start off at, say, a positive potential. Let's just say it's positive 1, and this is like negative 1. Sorry, negative 1. Let's erase this. Write a little bit better. So you have negative 1, maybe you have 0 here. And as you do cyclic voltammetry, maybe you start here and there's like nothing happening. This is 0. And all of a sudden, like you get some kind of peak, and then maybe you get something down, and maybe it doesn't like necessarily look super good. That won't happen. This shouldn't happen. But basically, you know, like, oh, some process is happening here. There's some process happening here, and these peaks will start to indicate the potential at with which your species is starting to deposit. And then conversely, also, as you sweep more positively, you'll start to see these peaks that might be associated with the oxidation of that electrode deposition process. So cyclic voltammetry really is going to be the key in determining what potential should you apply to get when doing electrode deposition. So hopefully that's helpful. Doing a cyclic voltammogram is probably the best thing to do. So Saeed, let me know if you have any further questions about that. Let me see. Okay. Okay. Ahmad is asking how we perform CV. Well, you'll need to use some software. You'll need a potentiostat to perform cyclic voltammetry. You'll need electrodes. You'll need a cell. You'll need a whole lot of stuff. Well, I can at least show you, Ahmad, I think I got that right. Please correct me if I'm wrong. As I can at least show you some of the experimental parameters. So let's just go. Can I not have a new? Well, yeah, I can actually show you. These are the experimental parameters that you need to adjust. And let's see if I can't make a copy of it right. So this might make it a little easier to demonstrate. But you can define the number of segments. Like once you set up your electrochemical cell, you just need to add whichever, you need to fill out these parameters. You need to figure out how many segments, which is like how many times is the potential going like up and down, up and down. You need to figure out what the initial potential is, your final potential, if there's a vertex potential. So, and then you need to figure out like how fast it's going. That's usually all you really need to know. And then just to kind of take it a little bit further, to give you a sense of what those parameters mean, let's just take a look at this, delete that. So the applied potential waveform looks like this. You have time, and then you have voltage. So you start at some voltage, you sweep it maybe linearly with time. Then you go here, and that's a cyclic voltammogram. This slope is the scan rate. That's your sweep rate. That's your sweep rate. This is the final potential. That's your final V. We'll just call it V. This is your vertex or switching potential. Vertex potential. And this is your initial. That's like what all those kind of correspond to. So initial. Maybe too many eyes. And that's it. That's usually all the things. So all those parameters like, oh, this is like 0.2 volts, and this is 0.5 volts, and this is plus 1 volt. Actually, no, this is actually like maybe this is 0.2 volts because it's like the same level. So that's kind of what it refers to. But you need all those experiments you need the experimental setup to do all of those things. So hopefully that was at least helpful in terms of what you need. I can elaborate further if you want, but Ahmad, hopefully that was helpful. Jam 2022. Let me see. So actually, I'm studying I think it's material science. Material science. I'm very much interested in electrochemistry. Can you take fundamental to advanced electrochemistry? Can you take fundamental to advanced electrochemistry? I saw many videos. All very nice. Well, thank you. I'm glad that you enjoyed those videos. I don't know what you mean by can you take fundamental to advanced. There are some electrochemistry courses out there. I don't know how good they are. They're all usually taught in some kind of graduate programs. Most of the time, I would say the basic electrochemistry course is already pretty advanced. But having done a lot of electrochemistry, I could see a full year course on electrochemistry. The first semester would be on DC voltammetry techniques. The second semester would be on like AC voltammetry techniques. That would be a year-long course in electrochemistry. But hopefully that's helpful. Let's see. So how can we perform CV on the coin cell? How to set multiple probes coming out from your workstation. So Ahmad, you would use the same thing, those same parameters that I mentioned. You have to, figure out what parameters work for your system, for your cell. What's the potential capacity of your coin cell? And then usually you need some kind of multi-channel potentiostat to have multiple connections to study and discharge multiple types of coin cells. So that requires a multi-channel potentiostat with lots of probes kind of coming out and allowing you to quickly charge and discharge coin cells effectively. So there may be some equipment that you need to perform some of that stuff. But all the parameters I told you for cyclic voltammetry, those apply to coin cells. It's just a matter of figuring out which ones you want to use it for if you're doing CV of a coin cell. All right, let's see. So this is from Anurada. I hope I got that right. How to standardize / calibrate the Pine RDE to verify that it's working and in good condition? It's a great question. Something that I actually know quite a bit about. So first and foremost, so maybe one thing to first clarify is when we talk about Pine RDE, we're talking about a Pine rotating disc electrode. And there is the rotator itself, and that doesn't actually really need to be calibrated. It's calibrated from the factory when it gets there. But and the only calibration associated with that instrument is calibration of the rotation rate. So if you suspect that your rotation rate is off, then that would be the time where it's like, okay, I need to test it and calibrate it. And we have a calibration kit for that. But what I think you're really asking for, and clarify with me if I'm wrong, is you want to know, how do I know that my electrode is good? All right, that's a good question. And Ahmad, I saw your comment. Thank you. I'm glad that the answers were very helpful. Okay, so your Pine RDE, maybe it's a glassy carbon or a gold RDE rotating disc electrode. So what you should do to verify it's in good working condition is just do a regular cyclic voltammetry test on a well-characterized redox couple, such as ruthenium hexamine or ferrocyanide or ferrocene if you're working in non-aqueous systems. And just make sure you can get kind of a regular looking duct. And when you're rotating, you get these nice Levitch S-shaped curves. So let me kind of show you a little bit what I mean by that. Is that, let's kind of delete this. Is that when you, there's actually a couple other things you can do. But for example, if you get a rotating disc electrode, I say just do a regular cyclic voltammetry experiment. You don't even need to rotate the electrode to make sure that the rotating disc electrode is fine. Make sure you're getting something like this. Make sure you do this, and then any new rotating or any new RDE tip that you get gives you the same kind of voltammogram. Similarly, if you you can also look for, hey, what happens if I rotate at say 1600 RPM, and I get these voltammograms that look something like this. Right? Well, you should be able to correlate the limiting current to the Levitch equation. So you can use the Levitch equation to kind of verify that, oh, the current that I'm measuring associated with the concentration of the species and the diffusion coefficient of that system is well behaved. And make sure you're getting curves like this. And that's really about it. Making sure that you're able to reproduce a normal cyclic voltammogram or a normal rotating disc electrode is the important thing to do to kind of standardize, making sure that the electrode is in good working order. So, Anurada, I hope that was helpful and answered your question. If you want to know more about, say, the rotator from how do you calibrate a rotator, for example, that's a different story. So, oh, it looks like we might have Neil coming on board. It's a maybe. It depends on how he's doing. But we've gotten through a lot of questions. I will continue.
Can you hear me?
Here.
Can you hear me?
Can't hear you, so we gotta.
Okay, one sec.
Oh yeah, he's just give him a second, everybody.
Hear me yet? Let's see. Wait.
And
audio input.
And Neil, if you also want to address any of the other previous questions, just tell me which ones showed up.
Can you hear me yet? Can you hear me yet?
Yes, I can hear you now.
Look at that.
Yeah, look at that. You're at RDU Airport now, right?
Yes, I'm at the airport. Just finally made it here. Thought I'd pop in and see how things are going.
Good. I think things are going relatively well. Of course, lots of questions on batteries.
On batteries, there's always
and
batteries.
galvanic stack charge discharge.
Always. It's the only thing that there's ever questions about, I think. It's pretty common, right? Are there any that, let's see, are there any that I can answer now? Are there any that were before that I missed because I've been in and out?
Yeah, so this is a new one from Ahmad. He wants to know a little bit more about two sides of a coin cell. Which probe should get attached to the positive side and which side to the negative side?
That's a good question. So the answer is when you are using a coin cell or a battery, the cathode is the plus side, the anode is the negative side. These are sort of the nomenclature that we use to talk about these two. It's somewhat arbitrary, to be honest, because like, as Alex and I have recently discussed in a very funny separate thing that only he will understand at the moment, there's a bit of strangeness with the naming convention, if you will, when it comes to anode and cathode. So for example, I can only assume that your question is probably related to a rechargeable battery, which means the designation of anode and cathode is somewhat silly because the cathode is described as such because it's the cathode, it's the cathodic side. Cathodic is reduction, right? And so that implies that it's a reduction occurring. Whereas the anode, anodic, implies oxidation, okay? Those are what's going on at each side, but that is designated as such when it is discharging only. Now, if you have a primary battery, like a regular battery that can't be recharged, that's all it does is discharge. So the cathode is reducing, the anode is oxidizing. and it's discharging. But of course, in a recharge of the battery, you will often charge it back up, right? And so when you're charging a battery, the exact opposite is occurring, which is to say that the cathode is oxidizing and the anode is reducing, which makes these terms kind of silly. The last part I'll say is that relation to your question, if you're using like a battery tester, it's usually pretty self-explanatory. You usually plug it in and you don't have to do many cabling or things like that. However, if you're using a potentiostat or something that does have cables, you know, the alligator clips and things like that, you want to connect the working electrode to the cathode and the counter arc reference electrode to the anode. That will give you the proper reading. You'll have a positive voltage, and when you have a negative current, it's discharging. When you have a positive current, it's charging. I hope that clears that up.
Very good, very good. So I'm answering. Anurada had a question about RDE, and I'm just sending her a link to our rotating disk electrode theory that should give her some just a little information about the kinds of curves she can create, possibly in doing a Levitch study for making sure the system's working. So that was a good one. We have another question from Jam 2022. It's probably one of my favorite topics.
Oh, it's an inductor.
How inductor and
electrochemical double layer.
I guess that's electrical double layer.
Double layer capacitance. Yeah.
Influence EIS. Double layer capacitance.
Inductors are Alex's favorite thing. Thank you for asking this question.
I know.
Go right ahead. Go right ahead. Or yeah, you can answer.
So
either way.
I can answer. I guess.
Actually, so okay. Before I let you go, to be fair, I don't think he's talking about inductive loops. This is just inductors, right?
That's true.
So,
yes.
I mean, inductance is usually just cell cable stuff. So actually, this is not a question that should trigger you. You can be calm.
Oh yeah, no, it doesn't. It doesn't trigger me actually in this case. This actually does not trigger me. But inductors are probably one of the only circuit elements that gives you a decrease in the impedance as the frequency decreases. They have has somewhat of an inverse relationship to capacitors. That also has to do with the relationship to phase as well. So inductors can be observed as, say, you get these loops, these inductive loops that we talk about, and that can affect the Nyquist plot that you see. And so that is how an inductor will affect the EIS. Additionally, inductors in the sense of cable inductance, which happens from just cell cables and instrumentation, you tend to get, you can get some interesting artifacts in the high frequency range associated with induction. So that affects the EIS. And then the electrical double layer capacitance, that in a way just affects the capacitor value, sort of say, that you get in EIS. And so if you have something like let's see, I'm sharing my screen, make sure the screen is properly shared because I messed it up last time.
Yeah, I'm glad I happened to be watching while you were doing that. I was like, wait, I don't see anything.
Otherwise, I would not have. I don't see anything. Happens to the best of us.
It does.
But you'll have one system, you'll have maybe one semicircle, and then if you have, say, another kind of if you have a different electrical double layer, for example, just making that red, you may have something that looks a little bit more like this. Maybe there's some charge transfer resistance and stuff like that, but really the value of the capacitor changes kind of how big the semicircle is. So that would be the other way you would see the effect of the electrical double layer in EIS. So hopefully that answers your.
Let me share and
yeah,
show a thing. Wait, window. Make sure I'm sharing too. Now that both of us are here, we can look after each other.
Mhm.
Is it working? Am I showing?
Yeah.
Okay.
You're good. Yep.
Okay.
It's good.
I want to clarify real quick about that. So just to illustrate, if this is the Nyquist plot, just basically what Alex showed too. Whoa, that's supposed to be a minus, not like the longest line you've ever seen. Minus. I'm working with a mouse at an airport, so give me a break here. Okay, zero. This is 0. So first of all, like Alex said, basically, if you have inductance, you'll usually see a little bit of line like that before you have your whatever proper sort of trace. So this is the inductance or inductor. If you have like a cable inductance, we're not talking about the presence of a possible kind of loop like that. That would also be an inductance. That's a different kind of odd phenomenon, and we're not going to get into that too heavily. For the most part, an inductive effect comes from cell cables. When you typically have very low resistance systems, the effect of an inductor of the cell cables will occur at high frequency, and it's mostly irrelevant. Like, it just occurs, you can kind of ignore it, but it's there. So it's good to know. And then just one clarification, it's not exactly that the double layer capacitance will increase, because remember, the width of the semicircle is proportionate to the resistance of your Randall's element. So actually, if this is your double layer right here, and this is your charge transfer resistance, the width of the semicircle changes RCT. What the CDL actually changes is not perceptible to your eye when you're looking at a Nyquist plot. What it actually does is it changes the distribution of points along this curve. Either they will concentrate more down here, or they will concentrate more over here. So, for example, if you have a, and I always forget this, if you have a very, let me, I will do one last sharing thing to show you and illustrate it.
That's good.
You bear with me here. This one, and then this one, and then click here, and then I click here. Okay, I did. Simulation. So, for example, if I have a simple Randall's element, I know you can't see the screen here, that doesn't matter. Okay, so if I have a Randall's element here, you see this semicircle, just push it away a little bit. All right, here's my semicircle, okay? So the effect, I'm not showing inductance right now, I'm just showing the resistance, charge transfer resistance and capacitance. As I increase the charge transfer resistance, the semicircle width increases. Now watch what happens as I change the capacitance. You don't see anything. Now the Nyquist plot at least, but it changes the peak and the Bode plot. And if I go extremely, extremely high, as in I have a very, very large double layer capacitance, what you could eventually see is that the semicircle doesn't complete itself, right? You'd have to go to even lower frequency. This is where you start to get into a position where there's some ambiguity. Is it capacitance or is it diffusion? Right, this kind of looks like a Warburg if you think about it. I know it's curved, but you can imagine this is, if you have something like this, it almost looks like a Warburg kind of an element. But really what I'm doing is I'm changing the distribution of the points along the semicircle. And over most normal, typical kinds of ranges, the semicircle still completes itself. And so you actually can't perceive the difference very easily. That's why circuit fitting is critical, and that's why if you have the Bode plot is critical. And the extreme on the other end, if you have a really, really small capacitance, is that it's like the semicircle doesn't start itself. So sometimes you see this kind of artifact, which is a variety of reasons, right? You see this sort of start like this, and then the rest of it begins. And it's almost like thinking about a really, really small capacitor that's almost irrelevant. And it's also a reference electrode thing that occurs sometimes, and that's the reason. But for the most part, the semicircle kind of behavior is what you're looking for to illustrate the presence of your electrochemical double layer capacitance.
Very good. Very good. Yeah, thank you. Because yeah, you're right. It's not the. I usually get confused with like it's both the resistance and the capacitor that
Yeah.
like changes the size of the semicircle. But if it's just the capacitor itself, that doesn't always manifest itself as
See,
like a size change.
you would be potentially, you could, there are situations, I think, and without getting into every possible specific circuit, like there's situations where that might be the case. Like if the circuit is more complicated, right? I think there's situations where changing this parameter or that parameter makes it, but I'm just sort of like the most basic thing, that's the behavior, right? But of course, there's other complicated versions of the circuit where you change the capacitor and this thing changes in a certain way. So what you showed might not be wrong for other situations, right? If the circuit was different or something like that.
Yeah. Okay. There is a question we got from the
Tiperuda.
Tiperuda. Sir, tell me about state of charge and state of health estimation of lithium batteries using EIS. I think this is probably, I feel to a certain degree with the state of charge is just how much it's charged. And then the health estimation of a lithium ion battery, I feel like that's based on looking at the state of charge, like the 80% state of charge over many cycles, and comparing how that's changing over time or over the number of cycles.
There's a lot of answers for what state of health means. It's actually not a term that has a definitive meaning. There's a lot of people doing research on different analyses for state of health. State of charge is straightforward, as you said. State of health is not. So state of charge typically is as simple as looking at a curve of capacity versus voltage. And if we look at this in the most simple dynamic, we could put 0 to 100%. So whatever the number is, right? This could be however many milliamp hours or whatever, how many coulombs, whatever it's irrelevant what the number is. If we just assume that is, and then here are our lower voltage limit and our upper voltage limit. Typical charge, discharge might look something like that. And then the discharge would be, I'm not drawing these very well because these plateaus should probably be a little closer together. But anyway, let's just work with my limited artistic ability for now. So essentially, the percentage, this is basically also state of charge. So the most simple kinds of battery diagnostic systems, and even yourself when you're doing a test, it's just looking at, well, okay, so there's two ways of doing this. One is that you just take the voltage. So if this is like 3 and this is 4, well, you can very simply say if it's at 3.3 volts, it's at 30% state of charge. That's like this is like the most, right? Obviously, it's 30% of the voltage between 3 and 4. Like that's one way to do it. That's more in line with how like your phone determines what its percentage of battery is left. It's a voltage reader. It knows about what the upper and lower limit is, and it's roughly linear over the bulk of the, this is mostly linear. So there's a, y equals mx plus b relationship here, and you can determine what the voltage is compared to what the state of charge is. Very simple. For you, when you're doing your analysis, you have this full data, so you can take into account, the ends and everything, and roughly speaking, hopefully what its capacitance is. It's from 0 to 100%. Let's say that this is a 1,000 milliamp hours, and I've put in 100 milliamps for 8 hours. I have 800 milliamp hours in. It's at 80% state of charge. Like, I hope I'm just using like the most simple numbers here to illustrate how this is hopefully pretty easy to grasp how you're calculating what the state of charge is of a battery at any moment, whether you're charging or discharging. That's roughly what it is. It's the other state of health estimation. Okay, so state of charge estimation using EIS is not really a thing. I mean, you can in some sense because the EIS spectrum will change with with the state of charge, but not as easy a diagnostic as the actual charge-discharge curve. Like you wouldn't use an impedance test under normal circumstances to get the state of charge of a battery. Like at 0% state of charge, you'll typically have a pretty big, however many, whatever your battery looks like, you'll have some amount of Randall's elements. And then typically at 100% state of charge, it'll be smaller. And the reason is that there's lower resistance here. This resistance is lower than the resistance at 0% because the battery is fully charged. It wants to deliver energy. It's easier to get energy out of a battery that's fully charged than it is in a battery that's fully discharged. So its resistance, charge transfer resistance, is quite low. But this isn't like a exactly always a linear thing. Like this semicircle won't grow like perfectly with state of charge, so you wouldn't use that. The state of health diagnostic, as I said in the beginning, is a much more nebulous concept. Sometimes what people will do, and actually I did this when I was a postdoc, for example, I was getting empirical correlations for certain aspects of the impedance data. For example, in my case, I think I used the negative imaginary impedance correlated with temperature. So it was like get a battery at some temperature, take impedance at some frequency, and then I can correlate like Zi versus temperature, right? And you get some linear or, I don't know, polymeric, quadratic or whatever relationship. What exponential? Yeah, what's polymeric really? What's the word I'm looking for? Polynomial. That's the word.
Like polynomial.
Words are hard sometimes. Yeah, polynomial. It's a polymer. It's like it's tough. So anyway, that's one relationship because the temperature of a battery falls under the umbrella of its health. For example, another version of its health is how much it's decayed. So that was what Alex said. For example, over time, you might have time, right? And you might have like percentage of its like maximum capacity. And so this is 100%, and over time, it'll start to decay, which means that as you start to discharge it or charge it, this curve starts doing this over time. You start getting less and less capacity over time at it. And so this is like 100% new battery. You get 100% charge and discharge. Like these are the same. But then eventually over time, you can only charge it up to here. You can only charge it up to here. You can only charge it up to here. And so now you have a new amount of measurement, which is to say this is only like 90%. This is only 80%. It's only 70% as like effective as it used to be. That's one version of the health, to say how much it's sort of not able to give you its full capacity anymore. And again, the state of health as it relates to impedance is difficult to define because there's different studies out there. People have correlated, for example, the impedance at maybe a particular frequency or at a particular time or at a particular, whatever. You do like 1,000 charge discharge cycles and it loses some capacity. And then you do an impedance test and you can do an empirical measurement that this impedance, the impedance magnitude changes after 1,000 cycles, and then it changes after another 1,000 cycles, and you can correlate that. And so that's what people are doing with that regard for what you've asked for. But again, it's not a set thing. The state of health is a nebulous term that just describes how the battery is doing. It could mean anything. It could be temperature. It could be, like I said, how much capacity it's lost. It could mean things like that. So it's less defined.
All right, very good. I think that was a very good clarification. So Kanav has a question, and I think he's running cyclic voltammetry. He has a question regarding characterization. I run one cycle in a lithium chlorate salt between negative 1.75 volts to plus 2.0 volts, simulating a cathode. And this time he wants to simulate what happens at the anode. So he wants to know if -1 to +1 seems fine. My initial thoughts are, if you want, there's actually kind of two questions, but if you have, if you're doing like a 3-volt battery, then the difference between like the positive, like the difference in voltage between the cathode and the anode in simulating needs to be, the voltage of the battery. So in this case, like 3 volts, because you have -1 to +2 or something like that. And so there's that. The other question or thought is, when it comes to simulating, like, could you measure the potential of the counter electrode during some of these other cyclic, these cycling experiments, by taking like a voltmeter, putting it between the reference and the counter to figure out what the opposite potential is that you need to run the anode at. So I guess that's some questions, but also ideas and thoughts about simulating anodes and cathodes.
I just don't think I understand the question fundamentally.
So
You're talking about running one cycle in lithium perchlorate. That's an electrolyte. You didn't say at all what your anode, what your electrode material is. I don't think I understand.
Yeah.
I don't really understand the question. You're also talking about voltages to cycle it between. Again, I think, yeah, it's not clear if this is like galvanostatic charge discharge or cyclic voltammetry, and then what are those voltages against?
Yeah.
What is the system? I actually don't know at all how to answer your question, Kanad, because you haven't provided enough information. In general, whether something acts as an anode or a cathode is, again, just a designation of what's oxidizing or what's reducing. So this is all a very logistical kind of thing, right? And where those terms are sort of silly, because if it's a cathode, it's sort of by definition defined as the thing that's reducing during a discharge process. Also, as a cathode, its fundamental, how do I put this? Its fundamental half reaction, its reduction, its fundamental half reaction, reduction reaction should have a positive potential, because that's what makes a battery have a positive voltage. It's E cathode minus E anode is the E cell. And when you make that arithmetic, you end up, like for a lithium ion battery, you end up with 3 or 4 volts or whatever. And that's because the reaction is like 3 volts minus a -1 volt, and you get 4 volts. Whatever the numbers work out, right? But it's like you don't get a negative number, because the cathode reduction reaction should be positive. The anode one should be slightly negative, give or take. And so when you make that subtraction, that's what you get. And so, again, with what you're talking about here, again, it's like the anode. You're defining your material as the thing that is undergoing an oxidation during a discharge process. So I think you clarified. You can give more information. The electrode materials, graphene coated graphite.
Yeah.
Is that like coffee flavored coffee? Graphene flavored graphite.
Yeah.
With
Exactly.
So your graphene isn't gonna.
And it sounds like it's a simulation kind of thing. Like he's trying to simulate what's happening on the anode and the cathode, and assuming that his, anode material is graphene, coffee flavored coffee, and then the cathode is mocha flavored mocha, or whatever.
Or platinum flavored platinum.
And he's just simulating like, oh, this, yeah, it's platinum flavored platinum.
Well, I just don't.
Which has always confused me, like, initially.
What's that? What, coffee flavored coffee?
Oh, like platinized platinum. Oh, like
platinized
platinum for the longest time. I'm like, why are you platinizing platinum? Isn't platinum already?
It's because it's more platinum than platinum.
It's more platinum. But yeah, I think that's just what he's doing as a study.
I mean, it's yeah. Again,
Three electrodes.
It's just confusing because what you're describing doesn't look like a battery. This is just a 3-electrode aqueous system. Like you can do some electrochemistry on a carbon electrode with a platinum counter electrode. This isn't necessarily a battery experiment. And in fact, in an aqueous system like this, you're not going to get any intercalation of lithium. I don't think that's what's likely going to happen in an aqueous electrolyte. You have to go to high enough. You have to have higher potentials for that to occur, which is only possible in non-aqueous, which is why lithium-ion batteries are non-aqueous. But I could be wrong. I could maybe not totally. I could maybe not understand your system, perhaps, and that might require. But I know you sent a. I think you said earlier you sent a manuscript to Alex. Maybe you can handle that offline.
Yeah. I got your email, Kanava. I'll send you, because I know it sounded like the manuscript, maybe the size was just too big and it bounced. I will send you a link to our, we have a cloud that you can send stuff. Flavored coffee. So yeah, I'll give you a link to like our Pine cloud that you can send. You can. It's like Dropbox. You could just drop the manuscript in. And I could take a look at it. So, okay. So there. Let's see. I don't know. How's your time looking, Neil?
I'm getting on an airplane in about an hour.
An hour.
So
okay.
Yeah, I got time.
All right. So you're good.
Yeah,
okay.
Because this thing's going to end.
So
in
I
about
think we
20
need to
minutes or
maybe
so.
know a little bit more information. Okay. Yeah. We'll probably end in about 20 minutes. We've gone through most of the questions. So Ahmad's asking. I think we might need to know a little bit more information, but I want to know about the shape of a CV graph, specifically the change in the shape of the graph. Like sometimes we observe a peak and sometimes a flat response. What kind of storage mechanism we relate with it? So to a degree, we need to know a little bit more about the electrochemical system because, Neil, I'm pretty sure people do CVs of you were talking, I think, earlier about supercapacitors and batteries and things like that. So I don't know if you're talking about a traditional 3-electrode cell, but always remember one thing, which is that if current is flowing in your electrochemical system, you're going to get some kind of, you're going to get current to flow. That is indicative. That'll make the current rise. And then if that rate of ions transferring decreases, it's going to go down and you'll get a peak. And that's what that's for. If you have kind of a background current that's like a square, and maybe it increases, or a rectangle, that's usually some kind of that's usually a capacitive process that manifests itself in the graph. So it's interesting that you ask what kind of storage mechanisms we can relate to it. I think we need to know a little bit more about your system.
Yeah, but what you just said is actually as an answer to that is if you have just sort of a envelope kind of a thing that scans back and forth and it's flat on the top, flat on the bottom, that storage is capacitance. That's the answer to that, right? That's either double layer capacitance, or if you're looking at a supercapacitive material, it's capacitance, right? So that is a charge storage mechanism. A peak is an indication of a charge transfer process, some redox process, right? That is experiencing some kinetic and diffusion limitation, diffusional processes. That's why you get a peak. Right, and so generally speaking, every cyclic voltammogram has a gap between the anodic and the cathodic scans, and the gap between those scans is related to the storage of some amount of charge in the electrochemical double layer. So that's maybe some of the answer to your question.
Yeah, I think we need to know a little bit more, but hopefully that's at least a little bit helpful. I think that is going to be a little bit longer for more questions, but I think those are all the main ones. Yeah, there's always a couple questions about galvanostatic charge discharge, and it's all making me feel like, oh, you know what, I might need to just take a battery and just start charging and discharging it and just seeing what the heck I get, and just so that I kind of know more about what people are asking about.
Yeah, it's one of those things that batteries are. I mean, when I started doing batteries in graduate school, I didn't. I also had no idea. I mean, I had no idea what I was doing, and it was hard to learn, and it was just something that like I wish this existed. I wish I could talk to me from 10 years ago or whatever, you know, because it's like you feel sort of like I'm just in the lab. I need to test this thing. I don't know how to make it. There's a lot of little like tips and things that you learn through experience about how to make the battery, how to make the coin cell, what order to do things that, you know, simply even reading the literature as much as you can doesn't help you learn. You know, you learn from if people will tell you, or you just sort of try out. There's a lot of trial and error, and a lot of the nomenclature and the jargon with battery people is very different from other normal, actually normal, electroanalytical chemistry people, I guess, you know, like stuff like that. So you know, it's tough, and I can understand why people are perhaps, I don't know, asking a lot of these kinds of questions, because it is sort of hard sometimes to find the answers out there. That's why I hope to try to draw some of these things for you. And again, I know there was previously some questions. I think I might have missed some today. There was one maybe from the comments on our YouTube channel, which hopefully next week, maybe or the week after. But when I'm back and able to really draw out some of these things, and I tried to answer some today. But if there's more questions about, like, for example, how do you calculate capacity, I could show you like the theoretical capacity, for example, for like carbon and where it comes from, how to get it, those kinds of things. Some of those calculations are things that you don't see very often. Actually, that was the one thing I just was showing. Kanav had this. I think that you are. I didn't hit it by accident, actually. I just said, isn't state of health in terms of phone batteries simply current capacity over the rated capacity? So that is one way. That's what I was trying to show, for example, with those curves where it's like, oh, it's getting further over, like it's, you know, its rated capacity is 1,000 milliamp hours, and now it's at 800 milliamp hours, and so it's 80%. Like state of health is 80%, you might say, or like it's. So yes, that's one of the ways that's classified or quantified, if you will. That is one of those answers to that. But again, state of health is more of a, like I said, it's a general umbrella term, and it could be quantified or measured or determined in a number of different ways, and that's just one. And don't worry about it with your phone. There will be a new iPhone out in about 45 minutes. You can just buy a new phone before your battery dies.
Yeah. It seems like there's always new phones with new batteries and constantly improving the technology. So, yeah, absolutely. Okay, I think that will about wrap it up for this week's Ask Us Anything About Electrochemistry live stream. I know school and stuff is starting to start, and people are getting back into the lab, or at least they're in the lab more. So I presume we may have more questions in the future, upcoming weeks, about stuff. Although actually, what is it? Looks like we got 2 questions. Do you want to answer them now, or you think we're in the?
I guess we can try to answer them now.
Yeah, we can answer some of them. Yeah,
a small chip on the phone calculate the amount of charge passed through it to the battery, and then basically relate it with the percentage showing. Are you talking about? I mean, if you're talking about adding something into your phone, that's a very bad idea. But unless you're a very good electrician, or you're you know how, you know, these phones are not even really open. I remember the days, which shows how old I am, when you could take out the battery of the phone and put a new one in, and it was a whole thing. Now the phones are not meant to be opened and accessed and whatever. I mean, in theory, what you're talking about could be possible to, I mean, you're talking about basically putting a very small voltmeter inside your battery in parallel, or excuse me, yes, in parallel to measure the current, and then you would use that for something. I mean, that's in theory possible, but it's probably not advisable as well for a number of reasons, because the phone itself is designed to take certain, you know, current and charge to work with its battery management system and everything like that. You could end up, it's possible that this could work. It's also possible you could cause some other sorts of algorithm damages or something like that that the phone's not prepared for. In theory, what you're talking about could work, but you know, I'm not sure that that's you mean that can companies use this to better display battery health to consumers?
I don't know. I mean, we already have like the percent battery. Like, what more could? It's like your typical consumer doesn't need to know what the Nyquist plot of
No,
their battery looks
it's
like.
not
They
about the
just need to
Nyquist
know,
plot.
do
So
I need to charge it or not?
I think thinking about this objectively, I think it's possible that could be done. And my guess is that they wouldn't want to do that. For one, I mean, what you're talking about is like, okay, so for example, the phone, there's a couple of ways that this is a problem. First of all, very rarely is your phone ever completely charged and discharged from 0 to 100 or 100 to 0. Okay, the reality of a phone is like the reality of a car. It's when you're doing charge discharge tests in the laboratory, you're going up and down from 0 to 100 and you're categorizing it. A car goes down, up, down, up, down, like your Tesla is driving, and you never really fully discharge it unless you die on the side of the road and you have to recharge it. So it's almost never going from 0 to 100. Same with your phone. You're using it or whatever, and then you plug it in halfway through the day to give you a little more juice, or you just go all day and you're at 46% when you get home, and then you go to sleep and you plug it in and you charge it back up. It's like there's some calculation that can be done there, but it's not the same, perhaps, full level of like, oh, I know exactly how much current was required to go from 0 to 100%. And that way I can give an accurate diagnosis. Now, maybe you'd be able to get some diagnosis, but it's probably not as complete because of the way that the phone is used. That's the first thing. The second thing is that what you see for the charge on your phone is not actually what it is. They limit it so that when your phone's dead, it's not actually dead. It's for emergency purposes. You can still use it. The third thing is that think about it from a marketing perspective. I think it's quite unlikely that the company would be likely to provide you some indicator that says, for example, your phone's state of health is 80% of what it was when it was new. Because then you're going to say to yourself, but I've only had it for 3 months. Why is the battery only 80%, whatever? There's no way that ends well for the phone manufacturers if they're honest about that information. Because you're less likely to notice that perhaps your phone died 17 minutes sooner when you used it fully without recharging it than it telling you that its capacity is slightly worse. So I just can't see a reason they would do that. And then also because you can't change the battery of the phone. Like you can't, I mean, I don't think you can anyway. Most modern smartphones, again, the battery is really pretty inaccessible. I don't think you can buy new batteries for phones. I don't believe you can. And the third thing is that it's just from a consumer perspective, is that part of this this whole calculus is that the consumer, unlike me, usually buys a new phone every 1 to 2 years. You're going to buy a phone before the battery is not giving you enough to use the phone within reason. You're going to buy a new phone because you want the new gadget. Most people are like that. And so there's no sense in telling you how crappy your battery is at any moment, because you're just going to want the new iPhone because it's a pretty new gadget. That's where the industry is right now. So for all those reasons, the answer to your question is probably that yes, they could, and no, they will never do it.
I also
September
just wonder,
12th.
like, how many people... Oh, he's gonna save date for a new...
The new iPhone. You know what's better than Apple? Anything else. Samsung. Android. I hate Apple products. I really do.
Okay. All right, we do have a question from Sleventh.
Seldom.
Can you tell me the difference between potential and frequency by practical way? And then there's kind of a little bit of a follow-up, and I think this has to do with my doubt regarding to EIS measurement. So to a certain degree, they are, in a way, related. I can share my screen and can talk a little bit about that. But because the potential that you apply to your system, right? Like when doing EIS, let's see if I remember. Because like the potential that's applied is equal, just I don't remember exactly, but there's like an amplitude, and let's say it's a sine wave, it can be a cosine wave, and it's like omega t, right? So oh wow, that needs to be fixed a little bit. Omega t, just like general, like the potential is what you apply. There's an amplitude associated with it, and maybe instead of calling it that, maybe a better symbol would be something like a E naught or an E prime. It's still like a potential, but this is the frequency. Omega here is the frequency, right? So that's what the frequency is. And if you have a sine wave, which you've seen, you can't draw sine waves super well.
Drawing sine waves is really hard.
But like drawing sine waves is very hard. But like how many cycles per second is the frequency? So maybe you have like, this is one hertz. So you have like that's like 1 hertz. This is 1 cycle, and that happened in, maybe let's just call it like it happened in 1 second. Like 1 cycle per second is the frequency. How fast is this happening? Maybe you have lots and lots of sine waves all squished into a smaller space, and I'm only drawing them small, but these could be bigger. Like the amplitude could certainly be bigger. I'm not drawing it super well because I can't draw sine waves. But like this has a bigger amplitude. That's the potential. This is a smaller amplitude. That's also the potential. So the potential and the frequency are related in a way to like, it's just how fast, how often are you getting these potentials to occur. So I hope that maybe makes it a little bit clear. Let me know if that made sense, just Sleventh, about the difference between potential and frequency, or kind of how they're related. Okay, so I think we answered that, and we have now talked about lots of battery stuff and electrolyte decomposition, and we're just having a conversation with Kanab at this point. So hopefully this answers all the questions.
Yeah. I remember issues from several years ago with the Samsung batteries. That there was one that caught fire somewhere. It was on an airplane, or it was something. It was a laptop caught fire. I don't know. There's been some issues, and it's always electrolyte decomposition. It's called thermal runaway. It's always the problem. So, but I like Samsung products. You're not going to convince me with these crazy things. They're not whatever. I don't care. I'd rather have a phone that catches fire and isn't Apple.
pretty extreme, man. It's pretty extreme.
I know. Listen, I don't care. I am what I am. I prefer what I prefer.
That's true. That's true. I can't make you somebody else.
That's correct.
Okay. Well, I think that's it. I think those are all the main questions. We've been going for about 2 hours now. So, Neil, I hope you have a safe trip, and everyone out there, I hope you have a good weekend or whatever time it is. There's if you're in the United States, Monday is is Labor Day, so we're off that day, and yeah, if you have any questions, we'll put something out on the YouTube channel. Make sure to follow us, and I think that is about it.